we've talked now about potential, the idea of potential. Let's actually calculate it. Let's calculate the potential near a point charge. And just to save me a lot of time and a lot of chalk and a lot of breath, from now on, the rest of the class, when I say potential, I mean the electric potential. I'm not going to say electric every time anymore. If I mean energy, I'll say potential energy. But if I just mean electric potential, I'm just going to call it potential. So there it is, just the potential. Okay? So we're going to start with a point charge, or we might say a sphere of charge. We can call it a sphere of charge plus Q. And have field lines coming out like this. Like that, and more field lines I like to draw like that. And let's think about the potential of a charge as it moves from point A to point B. Okay? So we're going from A to B. And first we want to calculate the change in potential energy. Okay, change in potential energy. We'll get to the potential in a minute. But first, the change in potential energy. So potential energy we usually label as delta U, and you have to be very specific about the 2 points. So we're going to talk about delta U if we took a little charge, a little test charge plus Q, from A to B. And even that is difficult when you think about energy. And one way to prove that is when I teach this class, and I have 300 of these brilliant little Rice freshman minds in here, I ask them the following very simple question. I walk into a coffee shop with $10, and I walk out with a cup of coffee and $8. What's the difference in my money? So here, you just shout out, what is the difference in my money? Walk in with 10, walk out with 8. And I bet you, if you're like all these brilliant Rice minds here, you said $2. And that's wrong, okay? You lost $2. The difference in your money is negative $2, if we're going to be technical, okay? So in the mathematical world, difference is always the final minus the initial, always, okay? So if I went from $10, if my final was $8, my initial was $10, it's minus $2. So you got to be careful with negative signs when you do changes in energy and changes in potential. Now, when we speak in language, we often have words that account for the negative sign. I went to the coffee shop and I lost $2. Well, the lost implies the negative sign. I blew $2, you know, et cetera. Blew means you exploded the $2. So all these numbers, all these words can give you the negative sign. But in physics, we can't just use a word. We have to actually make sure we have it right. So a difference is always final minus initial, okay? Let's see. So what is that energy going to be? If we go from here to here, if we just have the test charge here and just let it go, it's going to feel a force pushing it that way. It's going to naturally just fly from here to here. So in this sort of work and energy stuff, you got to think about the system, right? There's external and internal, all that. I'm not going to review that in great detail. But here, the system is the charge and the big charge and the little test charge and the fields they create, okay? So the system is doing the work. As the charge flies from here to here, the force is due to the system. So this is what's called internal work. The system does the work. When the system does the work, it's negative. The change in potential is negative work internal. Because if the system does this work, it's giving up some of its potential energy to do the work, right? That's why the change in potential is negative. It's losing some energy for the work that it does. So that one is negative W INT. So we calculate this work, and what is it? Well, we bring the negative along, and work is the integral from A to B of F dot ds. You might think of work as just F times X, but when you're really doing integrals and things are changing, it's the integral of F dot ds. So there's no inherent negative sign on this integral. Work is this integral, and I'm carrying the negative along. So then we just have to say, well, what's the force? The force is just the charge Q times the big field E. So we write it one more time. It's equal to the negative integral from A to B of the test charge Q E dot ds. And remember, the little DS's are the little steps we're taking as we go from A to B. There's your little DS. So you can look at this and decide if this looks right. So we aren't doing potential yet. We're still on energy. But we're saying that the energy should come out what? It should come out negative. We're losing energy. We're going from here. We're gaining a lot of kinetics, so we must be losing energy. So this thing should come out negative. It's got a negative sign there. That's a good sign. Will the integral come out positive? Yes. The charge is positive. The E field has a positive magnitude, and so does the ds. And they're in the same direction. Right? E and ds are together. So this integral is going to come out positive. There's a negative sign there. Therefore, the change in energy is negative. Everything's fine. Okay? So a long time ago in the golden age of Hollywood, there was a famous couple, Fred Astaire and Ginger Rogers, famous for dancing in the old movies, all this stuff. And there's a well-known quote that Ginger Rogers did everything Fred Astaire did, but backwards and in high heels. It's a well-known thing. Just to point out, it was actually harder for her. He got all the credit. He got paid more. She had to do it all backwards and in high heels. So we're going to do something similar in this problem. We calculated the change in potential energy, not the potential yet, potential energy going from A to B. Okay? Now we're going to do this. We're going to calculate it backwards. We're going to go from B to A because that will really help us illustrate what's going on. I think it'll solidify it in your mind. And I'm going to do it in high heels, just to go all the way. You know, I don't want to hold back and disappoint you. So I bought these this morning at a thrift store in Montrose. And nobody batted an eye. Let me see. Get this one on without falling down. Let's see. All right. Here we go. Okay, let's see. So we're going to go from B to A. And again, we're calculating the change in potential energy. Okay. All right. All right. So let's see. So now we're going to go a slightly different way. So let's not draw these DS's. That might change. Everything might change. We have our plus Q now sitting here going that way from B to A. So what is the delta U? So delta U, B to A, as we said before, that's the final minus initial. So it's the energy at A minus the energy at B. Okay? And that's equal to now a different work. Okay? So before, we just let the charge go. We sat it here and let the E field push it from A to B. Now there's actually a slightly different situation. It's sitting here and it wants to fly away. We're not going to let it. We're going to do external work. Okay? The agent that does external work has to push with an equal force to the electrostatic force and just a little bit more to make it move. But since it's an external agent doing work, the change in potential is positive. Before we had a negative here. Now it's positive because it's not the system doing the work. External agent does work. That increases the energy. Okay? So that's equal then to what? The integral from, in this case, B to A of F dot ds. And we can then say, okay, that's equal to the integral from B to A of the force. But what is the force? It's not just QE. The force is against QE. The system applies the force Q times the E field that way. To make the external agent, to make it move, has to apply force the other way. So a negative sign shows up in here, minus QE, there, dot ds. Okay. So let's see, do we think that's right? Well, this delta U had better go up. This thing had better be positive. This thing had better be positive. And it looks like it's negative, right? We have a negative sign right here. But guess what? E and ds are in a different direction now. So if you actually were to calculate the integral, you have E going this way, and you have ds going that way. So since they're opposite direction, this dot product will come out negative. It'll cancel that negative, and it will come out positive. Okay? So now we have our two delta U's. And I'm going to take these off because my calves are killing me. Okay? So now the question is, are they the same? Did we go two different directions and get physically the same answer? So let's think about it for a second. We said we know that we have delta U. We went A to B. And you know that if you go one way or the other way, they should be the opposite of each other. They should be negative of each other. So delta U A to B should equal negative delta U B to A. Right? Should give us the same thing. So let's take our delta U B to A and plug it in and see if we can get back to this. Okay? So we have a negative, and then delta U B to A was a negative integral. That negative sign, if we brought it out, would make that positive integral B to A of E, Q E dot ds. So now it looks like we have a problem, right? Because we know this thing is the negative integral of QE dot ds. But there's one more negative. There's so many negatives to keep up with. One more negative is that this integral is from B to A. It's going this way. This integral has the ds's going against the e's. So that'll bring in yet another negative sign. Or another way to think of it is we're going to flip the limits. If you flip the limits, you got to add another negative sign. That's equal to negative integral if we go from A to B of Q E dot ds. So if we plug in our value for B to A, keep up with all our negative signs, we actually get to the thing that was A to B. So all these negative signs are consistent. And I'm doing this in this level of detail because it's very hard to keep up with all these negative signs. And most textbooks actually don't get this detailed about it. They kind of gloss over it. And there's a bunch of negative signs and your 50-50 chance of getting it right. But if you look very carefully, they're all there. You got to think about which way forces are, who's pushing whom, which way the ds is, which way the limits are, but you can always get it right. And now, we completely understand the energy change. So next we'll start thinking about the actual potential, what we said we were going to calculate in the first place. We're finally there. We can now finally get the potential. You can see we've been thinking about differences in energy. So potential is the same way. It's not, to get these differences in energy, we had to know the magnitude of the test charge. And all potential is just saying, let's do it per unit magnitude of the test charge. So the potential, when you go from A to B, is simply defined as the change in energy when you go from A to B divided by that test charge. Okay? And then, if you want to write the integral, then it's minus the integral from A to B. And the Q is just gone, minus the integral from A to B of E dot ds. This is why, if you're reading a book and the first thing you see is they define the potential this way and you wonder why that negative is there, go through those previous videos. That will walk you through exactly why the negative is there. It's because where this comes from, this E dot ds, comes from the work you're having to do. Either that you're an external agent is doing or that the field is doing to move things around. That's where the E dot ds comes from if you think about the potential this way. Also, one more thing we could tack on there is that it's VB minus VA. Here, we have defined potential as a difference. What we've derived so far is that delta V from A to B equals minus integral of E dot ds from A to B. And really, that has nothing to do with a point charge. We've actually used a point charge to illustrate things, but this is just in general always true, what the potential is. That's how we define the potential. Now, I've erased my little A to B there, but here it could be anywhere. It could be A to B, from any A to any B. It could even be the same point, and you get no potential difference. Okay? So now, to really get the potential near a point charge, we have to actually plug in the formula for E and figure out what's going on. Okay? So let's see. Delta V then, the change in potential from A to B would be equal to minus the integral from A to B E. Well, E for a point charge, or for a sphere of charge, is KE times the charge over the radius squared times what? What makes it a vector? R hat. And it's that R hat that is dotted with ds. So our general expression seemed to make sense. The E field along ds, everything was fine. And now when you really apply it to a specific case, that starts to look weird. What exactly does that mean? So let's look at it. What would R hat dot ds mean? R hat would always be in this direction, and ds just depends on where you are, where you're walking around. Right? You could be going that way, you could be going that way, all these different directions. R hat is radially always out and has a unit magnitude. ds moves around, depends on where you're going. So r hat dot ds, basically in words, it's the component of ds in the radial direction. It's saying whatever path you're taking, for each step, how far are you moving radially? Because that's actually all that matters. In terms of potential, all that really matters is when you move along a field line, when you move out and go to a different electric field. If you move sideways, the potential is not going to change. So this is just picking off of all these little steps, how much is the radius changing? How much is your radius from the charge changing? Because that's all that matters. So what this tells us is that delta V, A to B, does not depend on path. It only depends on changes in the radius. Only on changes and that's due to the symmetry of the system. It's a point charge, E field lines go out. The E field only changes when you change radius. The E field doesn't change when you move around. So we could then write delta V A to B as minus the integral from A to B of K E Q over R squared. And we can basically take this dot product out, because what is it? It's changes in the radial direction. Its magnitude, this is 1, this is your step size ds. You can just put it together and call it dr. Okay? All that matters in a motion is, say if this is my ds right here, all that matters is we draw a radius here and we draw a radius here. All that matters is how much, if this is ds, did dr change. How much did r change? R changed dr. R changed an amount dr. So to write it and make it completely a scalar equation, it is a scalar because this is a dot product, but to take all the vector stuff out for a point charge, you can just call it dr. So there, finally, we've done what we said we were going to do. The potential near a point charge. Minus integral from A to B of K, Coulomb's constant, Q over R squared, dr. We have the potential, oh, we still have to do the integral. Oh my gosh, delta V A to B equals minus integral from A to B of KE Q over R squared dr. Got rid of all the nasty vector stuff and everything. Now we just do the integral. So this is R to the minus 2, so you bring it to the minus 1, divide by the minus 1, which makes that go away. So it's positive KEQ, and then it goes to R to the minus 2, R to the minus 1, 1 over R. And it's evaluated from, let's see, RB to RA. So we'll say the points A and B mean at the radius RA and at the radius RB. So if you want to evaluate that, then in the end, the actual potential, KE, Q, 1 over RB minus 1 over RA. So there it really is the potential difference near a point charge. If you go from any A or B, all you got to do is plug in their two radii here and here times KQ. And that's the potential difference. And it's in a unit, volts. The unit you might think of it being in is what? Is energy per coulomb, right? So you might think of it as joule, energy is in joules per coulomb, or we also call that a volt. Which we abbreviate with V, which is the same symbol we're about to start using for the potential, which gets a little confusing. But in terms of units, V is for volts, or you could call it a joule per coulomb. That's not very common. Every now and then, I have to fill out paperwork, either at the DMV to get my driver's license or health insurance or some awful reason. I have to fill out paperwork and I have to enter it. It says, how tall are you? And I have to enter my height. And that is just a terribly vague and stupid question, how tall are you? What does it even mean, how tall are you? I mean, if you look at me and if they just measure how tall I am, well, it depends. Right now I have nothing on my feet except socks, so I'm not that tall. If I wear my normal shoes, I'm up here maybe, right? If I wear my high heels, right, I'm way up here. So how tall you are is sort of a vague thing. They're really asking how high are you, right? They have that thing with the stick that comes down and measures where your head is. It's not a measure of how tall you are, that's a measure of how high you are, right? So if they really want to know medically, really the actual question, if they want to know my anatomy, the question is how long are you? Right? What they should really do is get you up, on a table, and they should measure you like this. You lay here and measure the difference between the bottom of my feet and the top of my head. That'd be how long are you. That would actually be relevant. So whenever I'm at the doctor or something and they want to measure this, my height, I say, no, let's measure how long I am. And I kind of lay, and then it doesn't go well from there. But the point is, these kind of measurements are difficult when they have to do with a difference. There's absolute measurements, and there's measurements that are a difference. And this is what's tricky with potential. Sometimes we write delta V, sometimes we just write V. Okay? This wasn't a problem with force and field. Force and field are absolute. If there's zero force, nothing will accelerate. Everything's fine. If you apply a force, the particle will accelerate. There's a very clear difference. Zero is special. When there's zero force, things don't move. When you talk about energy, it always depends. The potential energy, well, what's giving you the potential energy, and where are you relative to it, and can you get closer, or what are we calling zero, and does it go to infinity? All these sorts of things. So that's why it's confusing, is that energy is always relative. However, we do like to write it without that delta on there sort of all the time. So what we have to do is come up with what we all agree is zero, okay? When I go to the doctor's office and they say, how tall are you, and they want to measure it, we all agree that 0 is the 4. And the shoes is just a little error, they don't worry about it, okay? But it's like everyone agrees 0 is the 4. Right now I'm 5'11" from the floor. I'm about 15 feet from the floor of the basement, but we all agree the floor here is 0, so I'm 5'11". So let's see how we agree on this for electrostatics. So for a point charge, let's set U, the energy, potential energy, equal to 0, and therefore the potential equal to 0 at infinity, at R equals infinity. Now let's see then what this looks like mathematically. So we're going to have a charge, I'll draw it down here, plus Q, and we're looking on this axis. And to not think about difference, we're going to think about a point here, B, and then the point A we're going to put at infinity. Go all the way to infinity, and there's A, right there. Okay. So let's calculate that potential difference. So delta V, A to B, is a potential difference to go from A, where it's 0, all the way up to B. We just calculated what that is. That's KE Q times 1 over RB minus 1 over RA. Okay? And we know that's equal to the potential at B minus the potential at A. That's the definition of a difference. What we're trying to do is get a hold of this. Okay? So if we start plugging in things, we know that this special point A is infinity at the position R equals infinity. So this is 1 over infinity. So that's 0. That's 0 by math. Okay? That's not 0 because of what we said here. It's 0 because 1 over infinity is 0. So then we have KEQ times 1 over RB. That's what that side becomes. And now let's look over here. This equals VB minus VA. But this is 0. This is 0 by our definition. Define. So you don't want to mix those up. 1 is 0 mathematically. 1 is 0 because we said it's 0. Once you do that, you see the answer. The potential at any point B, really wherever you go, VB equals KE, and it's usually written like this, Q over RB. And usually we write it that way. It's not a potential difference. We all agree where the zero is. We don't have to think about difference anymore. Now you can kind of think of it as an absolute potential. In a world where it's 0 at infinity, you can have an absolute potential. It doesn't have to be a potential difference. As long as everybody agrees that that's the world you're in, as long as we all agree where the floor is, then it works. Okay? And it's a very simple expression to remember, kq over r. And it's not just true here, since RA is all the way out at infinity, it's true at any radius. And if you're in spherical symmetry, it's not just true in this direction, it's true in all directions. So really for a point charge or a sphere of charge, this is the potential in all space around the charge, because you're always not quite at infinity. We can also use this to get an idea that a coulomb is a lot of charge. You may remember one of the very first lectures, I told you that a coulomb is a lot of charge. So let's apply this formula real quick numerically and see that that's true. Say I had my Van de Graaff generator here. And let's just say it were to make a coulomb of charge. All right. And then, you know, I like to play with this stuff. Let's say that I'm sitting here a meter away. All right, there we go. Let's say I'm sitting here a meter away, like that. What potential would I be at just a meter away? So the potential here would be K, 9 times 10 to the 9, oops, Q, 1 coulomb over 1 meter, would be at 9 billion volts. Okay, we would definitely, you know, have some of this going on, or, you know, dead, right? 9 billion volts if you get a meter from a coulomb. In a real experiment, of course, the air would break down. Lots of things bad would happen before you got to 9 billion volts, and you couldn't really build up a coulomb. But the point is, a coulomb, huge amount of charge, creates huge fields and huge potentials. But we can now think, if we're careful, in terms of absolute potentials. We don't have to think always in terms of potential difference if we all agree where 0 is.